So this is the last day of our second workshop of the special year. And we start with Tsao-Hsien Chen from the University of Minnesota and IAS. He will talk about the derived Satake equivalence for symmetric varieties.
Thank you, Daniel. Thank you for the introductions. So, today I will talk about the joint project with David Nadler about derived Satake equivalence for symmetric varieties. So the goal is as follows. So in an ongoing project of Benzvi, Sakadarides, and Venkatesh, they on relative Langlands programs. So they propose many interesting conjectures. And one of the conjecture, which is they call the main local conjecture, is a generalization of the derived Satake equivalence for complex group to general spherical varieties. And so today I will explain an approach to this their conjectures in the case when the spherical variety is a symmetric variety, and using real groups. So more precisely, using so-called Beatty geometric Langlands for real groups over P1. So actually, in the case when the symmetric variety is just the group, so and this relation between derived Satake and the geometric Langlands for P1 is a result of Vincent Laforgue, and actually he gave a talk about this in the previous special year conference on in geometric representation theory, where I think Roman was the organizer. Okay, so first I will start with the case of derived Satake, the case of complex group, and explain this relation. So the relation between derived Satake and the geometric Langlands for P1. So let me begin with some notations. So let G be a complex Redati groups, and we have this loop group and the positive loop group, and the L minus G, which is a polynomial loop group of G, but with inverse parameter T inverse. And then we can form the quotients, namely the Frank-Grassmannian LG mod L plus G. And we also have the complex Langlands dual group of G. And I denote this Frank G check with a Lie algebra of the dual groups. And here is the statement of the geometric Satake equivalence to Lustig, Ginsburg, Markovich, Vilonen, Benson, Dreamfield, and also the derived Satake, and it's a derived generalization to Perspicamico and Finkelberg. So here, so the geometric Satake says that you can consider the category of perverse shifts, equivalent perverse shift on Frank-Grassmannian, and this is equivalence to a representation of G check as a tensor category, a fundamental result in geometric representation theory. And then there's a derived version of this here. So where the left-hand side is the whole equivalent derived category of Frank-Grassmannian, and the right-hand side is basically the derived category coherent shift on this this quotient. So G check star is the dual of the Langlands dual Lie algebra, and the G check must act on this by the adjoint actions. And you have this cohomology shift here. So more precisely, this guy is just the direct category of G check equivalent DG module over symmetric algebra of a G check, but you functions on this guy. So it's G check, but now the shift is -2. And we have a natural functors from here to here and here to here. Here is a natural inclusion, and here the map here is induced by the, so we have a natural map from this quotient to BG, and this map is given by the pullback. And so this is the statement of geometric Satake and also the derived Satake. So So this year we spent, this is one of the seminar topic this year. Okay. So now let me explain the relations between derived Satake and geometric Langlands for P1. So, or more precisely, maybe you'd like to call the Beatty geometric Langlands for P1. So let's consider P1 projecting line of the complex numbers. And we can consider the moduli stack of G bundles on P1. And so these bundles emit the following nice presentation. So it's basically, you can think of this as a double quotient. And you can identify this with the L minus G orbits on the quotient of the Frank-Grassmannian map via by this L minus G. Okay, and so, and then we have the following key diagram here. So in the bottom here, we have derived Satake. So I just explained the statement. And now observation here is that this category here is actually casudual to the category here. So you have to consider coherent shift on, so now on this quotient where you have a G check, but this space is G check, the dual Lie algebra, but in cohomology degree -1, and quotient out by the Langlands dual groups. So this is the casuduality. And then turns out one can interpret this quotient set. This is a DG stack. So first, this DG stack can be interpreted as this. So there, I should put the sorry, L, the derived intersections, point times point over G check square point to the map. You single point as the identity element of a G check. You take the derived tensor fiber product. Actually, you get you get this one, and then this the DG stack here turns out admit the following moduli interpretation. Turns out you can identify, think of this as the derived Beatty local system on S2. S2 is the sphere. So namely, one way to see this is that you can think of S2 as a union of the two-dimensional disk, and where intersection is X1. So therefore, this local system can be think of as you have a local system on two disks. When you restrict to the intersection, which is S1, they agree with each other. So this is one way to see these identifications. So the underlying scheme is just BG, but you have some derived structure, some nilpotents. Okay. And once you, so here's the one observations here. You can think of under casuduality, the spectral side, the coherent side on the derived Satake can be interpreted as just a direct category coherent shift on this derived Beatty moduli space. And on the other hand, on this side, the constructible side, turns out the derived Satake category is equivalent to the direct category of constructible shift on moduli space of G bundles on P1. So more precisely, because of this presentation, this category here is the same as direct category on this quotient stack. And turns out this quotient stack, the category here is equivalent to the direct Satake category. And so here, the equivalence here between this quotient and the direct Satake category and these quotients is a result of Vincent Lafort, and it's given by this correspondence. So you have these quotients, and you can pull back to G mod of Frank-Grassmannian, and you have natural projection to L minus G mod, so a Frank-Grassmannian mod L minus G. And this function, the equivalence here is quite concrete. You just consider pull-push along this Grassmannian. And you prove that this is equivalence. And so the proof is based on the Braden's hyperbolic localization or construction principle, applying to the natural GM rotation action on the affine Grassmannian, where the L plus G orbits are the ascending space, and the L minus G orbit on a Grassmannian are the descending space. So it turns out it's a very nice application of this contraction principle. And so therefore, we get this diagram here, relate geometric Langlands, or you like Beatty geometric Langlands for P1 and the derived Satake. So in other words, proving derived Satake is basically the same as proving Beatty geometric Langlands for P1. So that's the case for complex group, the relation between derived Satake and the geometric Langlands for P1. And so now, so basically the goal of this talk is to explain a similar diagram here in the case of a symmetric variety, where you replace the group by symmetric variety, and then explain a computation of this category using this diagram, using so here it turns out will be a geometric Langlands for the real groups, and I will try to explain how to use this diagram to do some computation for the derived Satake category for symmetric variety. So that's the goal of my talk. Okay, so now let's move to start to talk about the case of symmetric variety. So derived Satake for symmetric variety. So let me first remind you the definition. So let's theta be algebraic involutions on your group, and let K be the fixed point, which is usually called a symmetric subgroup, and the X be the quotient G mark K, the corresponding symmetric variety. So here's some examples. You can consider this case when G is a GON, and the K is the orthogonal group where the involution is given by this. So it's a transpose inverse. So this is a very important example of symmetric pair. And another pair is the symplectic group inside GO2N. So you have a GO2N, and you consider these involutions here, and then you get the symplectic group. So we'll talk about this example later in more detail. And now if I give you a symmetric variety, so first you can consider the loop space of the symmetric variety of X. And because the group acts on, the G acts on the symmetric variety, so in particular, the positive loop group also acts on this loop space. And some well-known fact is that the orbits, the L plus G orbit on the loop space is actually discrete. And I admit a very nice parameterization. So it's given by the dominant co-weight for a maxima split torus inside G. So maxima split here means that the involution acts by inverse. So we have this nice parameterization of orbits. And then for derived Satake, the main player here will be this category, this equivalent derived category for the L plus G action on the loop space of symmetric variety. That will be the main player here. And this is a very interesting but also complicated category. And we know before there's a conjecture by Benzevi, Sakalaridis, and Vegetash, we know very little about this category. So for example, So inside this category, you can consider the category perverse shift on these quotients. And I think we know very little about this category, but turns out there's you can define certain block, certain subcategory of these perverse shifts. And turns out you can, so a result of Gascory and Nadler, they show that one can define certain subcategory here inside the perverse shift on these quotients. Turns out which is it's a tensor category and is isomorphic to representation of certain group, GX check. I think now people call this Gascory Nadler dual group associated to this symmetric variety. So this is this group is a subgroup of the dual groups, and here are some examples. So sometimes this is equal to the original dual group, but sometimes it's smaller. And here are some examples. So when our symmetric variety is in this case the orthogonal group case, then turns out the dual group is the same as the original, the same as the dual group for GON. But for symplectic case, the dual group is GOM. It's a subgroup of GO2N. You diagonal invade. Okay. And so we know something about this category, namely there's some nice tensor category inside this category, which is isomorphic to the representation of these Gascory Nadler dual groups. But still, for the purpose of derived Satake, we want to. It would be great if we can have a full description of this equivalent derived category. Okay. And that's the statement of this the conjecture of Benz V and Sakadaridis and attached. So here is the conjecture. So they turns out they conjecture that actually this category, the derived Satake category for spherical variety is equivalent to derived category cohesion on quotient stack, where Vx check is certain gradient representations of the dual group, the Gascory Nadler dual groups. So it means that it has some cohomology shift here, and also some inner grading here. And you can form the quotient stack. And then turns out the conjecture that this category is equivalent to cohesion on this quotient stack. So it looks very similar to the case of the answer here looks very similar to the case of complex group. And for example, in the case of in a group case, namely G is GON times GON, and K is the diagonal GON. This is usually recover the case of complex group, because the corresponding symmetric space is just group G. And then in this case, the dual group is GON, and this Vx is just the dual of GON, which is GON, but you have to take the dual, and the degree shift here is 2. And in the case of symplectic group, so the dual group is GOM, which is kind of half of GO2N. And later I will explain that somehow we expect that this representation is the Vx here is GON, but we'll take a dual, but when the cohomology shift is double. So, okay, there's some examples of the dual group and these conjectural representations of these dual groups. And you can find, for example, there's a list of example of this G check X and this representation. For example, you can find a list in Yanni's papers. And let me just mention that, so they also so they make this conjecture, and they also relate this conjecture with periods and L functions. Let me just mention that turns out this cohomology, this shift here has something to do with special values of L functions. But I won't say more about this. But it's a very interesting connections. Okay, so that's the conjectural generalization of a derived Satake for symmetric variety. But let me just make the following remark. Actually, their conjectures is in a more general setting of a spherical variety, so not just symmetric variety. For example, you can consider the case when X is Gma H, where H is a general spherical subgroup. So spherical variety means that this you can see this variety has an open V orbits. Okay. And turns out in this setting there are some known case of these conjectures. So this work of Braverman, Finkelberg, Ginsberg, and Roman Trafkin, and here is Braverman, Finkelberg, Roman Trafkin. So here they consider this spherical pair, and also this case. And so in those cases, the dual group is G check, and this is the representation. So it's a cotangent of the standard representation times the standard representation of the dual groups. And same here. So you have the dual group is the same as the dual group of G, and the representation Vx. Sorry, I should put a check here. Is the cotangent of standard tensor standard, and with some cohomology shift. Okay, so their conjecture is in a more general setting, but today I focus on the case when this the case of symmetric variety, and one special thing about symmetric variety is that turns out well, this observation goes back to, wow, this is a well-known Cartan classification of a real form of a group, namely symmetric variety corresponds to real groups. So let me first remind you the statement. So if I have a symmetric pair, where K is a fixed point of algebraic involution, and turns out this symmetric pair corresponds to a real groups. So namely, if you basically, if you have a theta, you can always find a compact real form of your group such that, or in other words, you can find a compact real form and also a real form of your group such that their composition, they commute with each other, and they define the algebraic involution, which is equal to the theta, the one corresponds to this symmetric subgroup. So in other words, you can find, if I fix theta, you can find a real form such that they commute with each other, and their composition is equal to a compact, is equal to a conjugation whose fixed point is a compact real form of your complex group. And they are related by this diagram. So you have a compact real form, and you can find a real form of your group G, and turns out there's a corresponding symmetric subgroup such that the corresponding involution and conjugations satisfy this property, and their intersection here is a compact, the maxima compact of your real groups. And so here are the examples. So if you consider the case of orthogonal groups, then the compact real form is a unitary group, and the corresponding real group is the real GON, the GON over the real numbers. And their intersection is the real orthogonal groups. And in the case of symplectic groups, turns out the corresponding real groups is the GON, but over the quaternion. H is a quaternion. And let me just mention that, so quaternion is like the size of quaternion is like twice of the complex number. And turns out this observation will this has something to, later you'll see that this has something to do with the fact that in the previous examples, I say that the conjectural representation is a GON, but with degree kind of double is 4. So it's like the case of group case, but the cohomology degree here is twice as the complex group case. Turns out this has something to do with the fact that the corresponding real groups is a GON over the quaternion. Okay, so here are 2 examples of a symmetric pair and the corresponding real groups. And now, now I want to relate the derived Satake for symmetric variety with a version of geometric Langlands for real groups. So here so for this, I have to fix a real form on the projective plane. So let's consider the split real form on P1, which is given by conjugations. And turns out if I have a real form on P1 and a real form of your complex group, then you can define a real form of the stack of G bundles on P1. So basically it consists of a pair E and sigma, where E is a G bundles on P1, and sigma is isomorphism of your E and the conjugation of your G bundle. Namely, if I have a G bundle and this conjugation on P1, you can pull back and you get another. Well, you get a G bundle, but now it's not algebraic; it's anti-holomorphic. But then you twist the G by the conjugations for the complex conjugation for G. You do this twist twice, you get another algebraic G bundles on P1, and you assume that there's isomorphism and the square is identity. So basically, this is how you define a real. If I give you a real form on P1 and the real form of your complex, so you can define the real form of the bundle, modulus G bundles on P1. That's the main player for the geometric Langlands for real groups. And so here are some fact and result about this real forms. So turns out this real form, this G bundle here, admit the following nice presentation. Just like the case of complex through G bundles on P1, admit this nice double coset presentations. So let me first explain the case, the generalization that presentation to the case of a real form. So you can consider first the polynomial loop group for G, and then you can consider real polynomial loop groups. So namely, you consider those map gamma, where we think of this as a polynomial map from C star to G, and it maps the S1 to GR, to your real group. So make the unit circle to GR. So this is a real form of this polynomial loop group, usually called the real polynomial loop group. And now for simplicity, let's assume that the corresponding symmetric subgroup K is connected, and which is equivalent to saying that this real group is connected. So in general, you take a fixed point. Usually the fixed point will not be connected, but let's assume that K is connected. And so then turns out we have the following result. So it's a joint work with Nadler. So turns out this real form admit the following presentation is isomorphic to the corresponding mod this real polynomial loop group. So that's the first result. And the second result, which is some sense the main result here, is that you can consider the category of direct category consortative shift on these real bundles, modulus space or real bundles. And because of this presentation is the same as the direct category of LGR equivalent shifts on the Frank-Grassmannian. And turns out this category is equivalent to the derived Satake category for the symmetric variety. So here, so therefore we have this equivalence relating derived Satake category for symmetric variety, which is, so here everything is algebraic, but with the modular stack of real bundles on P1, which is real algebraic. And so let me say a little bit more about those, the proof of those two results. So turns out part one is an exercise about uniformization of real bundles. So basically, so the idea is that, so you can, so if we have this presentation, it means that we have this map from Grassmannian to this quotient, and this map is given as follows. So it's a bundles P1. So start with element in a Van Grassmannian, how to get the real bundle. So basically, you think of a Van Grassmannian as a bundle with bundles on P1 with trivialization on P1 minus, say, a complex number, say I, imaginary number I. Then you apply the conjugation, split conjugation on P1, you get you will get another bundles, but now on P1 minus I, and we together with the trivializations. And you can glue these two bundles, one on P1 minus I, another is P1 minus I, to get another bundles. You glue together, you get a bundle, and you can check that these bundles, using the trivialization, then you can show that this bundle actually has a real structure. So that's the map, the uniformizations map from GR to real bundles. Okay, and now the second, the equivalence here, which is some of the main observations relating shifts on real bundles and the derived Satake category. So this equivalence is given by push along the following correspondence. So it's very similar to the case of complex group. So you have this quotient step of Van Grassmannian by the real polynomial loop groups, and you can pull back. So we have a map from the quotient of Van Grassmannian by the real polynomial loop group for the compact real form of GR of a natural projection. And we also have a projection from this quotient to the Van Grassmannian, the formal loop group of K, which you can identify in this case under this assumption. You can identify with this one, and hence the L plus the quotient of the loop space of a symmetric variety by the positive loop group of G. So therefore, you have this correspondence relate the quotient of Van Grassmannian by a real loop group and the quotient of the loop space of symmetric space variety, symmetric variety by the positive loop group, and the functor here is just given by push along this correspondence. And the proof of this fact relies on a construction of certain, so LK are invariant Morse floor on the Van Grassmannian with LGR orbits, the ascending space, and the LK orbits, the descending space. So in the case of a complex group, the corresponding statement is a result of Lafouk is based on the construction. It's based on the construction principle and its natural GM actions on Van Grassmannian. And in this case, in a symmetric case, it relies on this construction of certain flow on Van Grassmannian with this property that GR orbit are the ascending space and the LKR orbits on the descending space. And let me just mention that this flow is real analytic, but not algebraic. And that's expected because somehow the equivalence here relate things on real algebraic. shifts on real bundles, but which is real algebraic. But here is derived Satake category, which is algebraic. Okay, so that's the relation between derived Satake category and shifts on real bundles. And now I can state the so recall in the case of complex group, we have this diagram relating derived Satake and geometric Langlands for P1. So now we can state a similar diagram here in the case of symmetric variety. But before maybe, maybe just add a few remarks before we talk about this diagram. So the equivalence here relating derived Satake category for symmetric variety and the shifts on real bundle. So, well, on the one hand, is can be thought as a real and a symmetric version of Laforgue's equivalence, and so relating shifts on bundles on P1 and the derived Satake category. And on the other hand, can be thought as a fine generalization of so-called Matsuki correspondence, relating this kind of finite dimensional and relating direct category of GR equivalent shifts on the flat manifold and the K equivalent shift on the flat manifold. So this is a well-known, very well-known result for in the case of a finite flat manifolds, and this is due to Markovich, Vilonen, and Usawa. It's a conjecture of Kashiwara, and so this equation somehow relate to GK modules and real group representations, and so and their proof is also based on a construction of certain Morse flow on the flat manifold, where the descending space are GR orbits on flat manifold and the ascending space are K orbits on flat manifold. And once you have this Braden's hyperbolic localization will imply this equivalence. And here's some nice pictures in this case. So in the case of SO2, then the Morse flow looks like this. And so here are the SO2 orbits. So it's upper hemisphere, lower hemisphere, and the S1. And here are the SO2C orbit, which is the K in this case, where you have North Pole, South Pole, and their complement. And they correspond to, at the level orbit, people said this GR orbit corresponds to this GR orbit corresponds to this, and this GR orbit corresponds to this. Okay. So so this is some remarks about this equivalence. So now let me. So any questions at this point? Sorry, I should. You good? Okay. So let me. Okay. So now here's the main diagram. So in the bottom line here, we have the derived Satake for symmetric variety. So here we have this derived Satake category. And here, the conjecturally, this category is equivalent to direct category on VX ma GX, where VX is some Grady representations. Now, so the conjecture, so we conjecture that we have a diagram like this. So first, we have there's a version of geometric Langlands for real groups GR over P1. So where the left-hand side is a shift on real bundles, and the right-hand side is we have so conjecture there's a spectral distribution of this guy, and it should be coherent shift on certain real form of Betti local system on S2, some certain derived Betti local system on S2, the real form of this. And moreover, this real phone should meet the following presentation. It's isomorphic to V check N mod G check N. So here, so this log 6 S2R is a certain real form of log 6 G check S2. And here, and this real form should meet the following presentation. So here, this G check N here is the dual group for GR, the real group constructed by Nadler in his PhD thesis using the real of Grassmannian. And turns out this real group is the same as the Gaston Nadler real group for the corresponding symmetric variety, the non-trivial result. And this conjecture C here says that this moduli space here is isomorphic to Vn check mod Gn check, where Vn check is certain gradient representation of this dual group for Gn check, the dual group constructed by Nadler using real of Grassmannian. And conjecture D here is just saying that these two categories should pursue dual to each other. Okay, so this the statement on the right, and on the left here is the result I just mentioned. So A and B are the equivalents in the previous theorem. So here is the presentations of your real bundle, and this is the equivalence I talked about before. And there should be a diagram like this, somehow relate the derived Satake for symmetric variety and the geometric Langlands for the corresponding real group over P1. So that's the main diagram in the case of symmetric variety, which should be think of as a generalization of the previous diagram in the complex group to the symmetric case. Okay, so any questions?
There is a question in the chat.
Sure.
And he's asking, how is N related to X?
How is N related to what?
To X.
Oh, yeah, sorry. So N here stands for Nadler. So Gn checks is is certain subgroup of the dual group constructed using real of Grassmannian. Okay, so it's his PhD thesis. And turns out a non-trivial fact. So it turns out you start with the real group, you can consider the real of Grassmannian. And turns out he can define certain tensor Tanalian subcategory of shifts on real of Grassmannian and prove that this is equivalent to certain representation of certain subgroup of the dual group. And on the other hand, later, Nadler and Gascoigne, they consider the more general case of spherical variety X, in particular symmetric variety. They also construct using basically this quotient. They construct certain Tannakian subcategory of for this derived category, and they prove that it's isomorphic to representation of certain subgroup of the dual group. And turns out in the case of symmetric variety, those two groups are the same.
Okay. Sorry, in this diagram, can you say again which arrows are conjectural and which arrow are not?
I think all the green one are conjecture. So this is a conjecture, and this is conjecture, this is conjecture, and this is conjecture. Yes. And these are on this constructible side is a theorem. Yes. So basically, you can prove, so basically this diagram say that proving derived Satake is basically the same as proving this version, this geometric Langlands for real group over P1. Okay, any other questions? Okay, so now I want to explain how to use this this diagram to say something about this category. Okay, so there will be. Yeah, so here's some remarks. So conjecture T says that. So this here is the causal duality. Okay, so a few remarks. So as applications of this diagram, turns out we also get an equivalence between the derived Satake category for the symmetric variety and the real derived Satake category for the real Grassmannian. It's a application of this equivalence. So I think Nader talked about this in the previous conference. And so in particular, it's interesting to know that turns out the derived Satake for the symmetric variety is in some sense equivalent to proving derived Satake for the corresponding real groups. So and yes, so this is an application of this the equivalence here. And there are another remark saying basically there's a variation of this conjecture where here we consider the split real form on P1. You can consider other real form on P1, for example, the antipodal map. And there's a version of this conjecture in that setting. And also there's a Temin ramified version of this where you replace, for example, you replace this L plus G by the Iwahori. But I won't talk about this. Okay, so now let's consider examples. So now let's focus on this symplectic case where G is a GO2N, the K is a simplex subgroup, and the corresponding real group is a GON over the quaternion. So in this case, we know that the dual group here is the GON, which is kind of half of a GO2M. And so with Nader, we do the following computation. So usually in the proof of a derived Satake, for example, in the case of complex group, a key step is to usually compute this extension algebra, usually called the equivalentized extension algebra for the category. So basically consider the base point and you convolve this with a regular representation of your dual groups, GX, and you compute the extension algebra for this category, the derived Satake category for symmetric variety. So these are key computations. And turns out we can use this diagram, or more precisely, these applications to show that this extension algebra first is the same as the corresponding extension algebra for the real Grassmannian. And then you can use, and then turns out it's equal to symmetric algebra of GON, but with this cohomology shift -4. So it's interesting to know that if you replace so here this real group is GN over the quaternion. If you do the same computation in the case of when you replace GH by the complex number, it's the usual derived Satake. And here you will get the symmetric algebra of GON, but with cohomology shift -2. But because somehow we're in the quaternion case, which I mentioned before, the quaternion is like twice of a complex number. Turns out you get this degree double, -4. And so this is a key computation here. And this computation suggests that suggests the following diagram. So in this particular case, the diagram should look like this. So here, the right-hand side, the conjecture derived Satake should be, so the Vx, the representation should be GON, the dual, but with degree 4 because of this. And it's causal dual to GON, which is -3 over GON. So namely, this Vnx is GON, but with cohomology shift -3. this quotient stack should be the conjectural the real form of a local system on S2. And we have so here's the should be the real Langlands for P1 in this case. And here is the derived Satake, the precise statement of derived Satake for symmetric variety in this case. And notice that, so in this case, you see that this real form of local system is like this. So it's equal to this quotient, GON, with a shift -3 marked by GOM by the adjoint action. And turns out this quotient is the same as just GON local system on S4, the fourth sphere, which is twice as S2. And one way to see this is that, well, S4 is like, you can D4 4-dimensional, this union 4-dimensional, where the intersection is S3. And so from this, you see that this local system, derived Betti local system is like, it's like this derived tensor product, and which can be, oh, there's some, yes, which can be identified with G with a cohomology shift -3 mod G. You apply this to this observation to this case, GRN case, you get this restriction. And so, and this is the conjectural spectral side. And our computation here suggests that this is the diagram, the conjecture diagram in the previous case here in the symplectic case looks like this. And so now let me mention that the proof, somehow the proof of this was inspired by modular representation theory. So basically, so in the proof of derived Satake for complex group, say, so for example, the proof by Roman and Finkelberg, he used, so basically there are two key computations. First is the computation of this extension algebra. And the second step is the formality result of certain DG algebra. And so the computation here usually use the result Ginsburg about fully faithfulness of equivalent cohomology. And this proof require, say, Hodge theory or theory of weight, usually. But so therefore you can, so if you want to use the real affine Grassmannian to do this kind of computation using equivalent cohomology, you can apply this directly because we don't have a Hodge theory or theory of weight in the real setting. But turns out there's this fully faithfulness, there's a topological proof of this fully faithfulness of equivalent cohomology in this particular case, in the case of complex of Grassmannian, just without Hodge theory. And actually this proof works also in a modular setting. And turns out that proof can be applied to the real affine Grassmannian setting. So in other words, there's a topological proof of this fully faithfulness or equivalent cohomology in this particular example for real affine Grassmann, and also in the complex Grassmannian. So you can apply that proof in this case and get this result. And in general, we because now I think Roman and maybe Arinkin, they announced a proof for derived Satake in a modular setting, and I believe the proof should be topological. So there's a hope that there's a purely topological proof of derived Satake in a complex group setting, and this suggests that there should be a, and the hope is that maybe the technique that can be applied also to this kind of the real setting, and then one can use this the equivalence between real and the symmetric to approach to understand the derived Satake category for symmetric variety. Okay, so now let me finally mention something I learned recently. So turns out in this particular case, there's a conjecture answer for the for this derived Satake, which looks a little different. So namely, so if you consider the symmetric variety corresponding to symplectic group, you can consider its cotangent, which is a Hamiltonian G space for the groups. And I think so. In their conjecture, this Benz-V, Sakarides and Venkatesh, they propose certain duality of a Hamiltonian G space, and the dual of this, the symplectic symplectic case should be is like this. So it's a cotangent of a GOM model, GOM diagonal, but you have to do Whittaker reductions along this upper triangular GOM. And usually, so here I think they say that this is like here you have a symplectic period, and it's dual to the so-called Jaquet-Shalika periods. And this has something to do with the fact that this symmetric variety is not tempered. And so it's a very interesting. So I think so. This conjecture answer suggests that this computation here somehow you won't see somehow from this computation you won't see this Whittaker Whittaker reduction here. I think it has something to do with the fact that this is a non-tempered. So maybe you have to consider some big category on this thing. Then you will see this Whittaker phenomena. But somehow you won't see this from these computations. And so now with Nether, we try to understand this phenomenon. This has something to do with SL2 after SL2, but at this point we still a mystery for us. So okay, so this is the final remark, and so let me go back to this. Let me to this page, and I will stop here.
Thank you for this very nice talk. Are there any questions?
You had a slide. I don't know if you talked about it, where mentioning what happens for the other real form of P1.
Yes.
Could you
yes.
could you say a bit more about this?
Yes. So yes, here. Yeah. Somehow in this case is something simpler. So you can consider, for example, the P1, but with relevance RP2. So now the involution has no fixed point. Unlike the split case, you have fixed point, which is the S1 or R. Yeah, in this case, the conjecture is more precise. Namely, in that case, we have there's a conjectural description of this spectral side, which is just so basically in this case, you can consider there's some extension of the dual groups by Z2, and you can consider derived stack of this extension local system RP2 such that the induced Z2 torsor is isomorphic to this Z2 torsor P1 to RP2. And that's we have a very concrete description of this conjecture in that case when you replace a real form by the antipodal. And I think Nader and Benz-V, they made some progress about this conjecture in that case, and also with Temi ramification. In particular, in that case, one can use this to really prove some version of this derived Satake. But in our case, when you have split conjugations, because of this fixed point, the construction of this is still conjectural. I should say highly non-trivial, because there should be some construction of this thing which is independent of everything. And then one can, just like the complex group case, you think of this local system correctly, you see this derived structure, this adjoint citation just appears naturally. And so there should be a construction of this which is equivalent, which is isomorphic to quotient and like this, and should be custodial to your the conjecture answer. So the hope is to see this mysterious presentation from some construction here. And you see that this is really something non-trivial, because, for example, you see this dual group somewhere in this construction, and this dual group is very mysterious. So therefore, this case is more mysterious than the case when you consider other real form of P1.
But you also say you might have this non-split extension. Is that right?
Yes,
you
yes.
see,
And
that's
yes.
also very interesting.
Yeah, that's also some very interesting some fine point, because basically it has something to do I think, for example, I think Bernstein has some note about this sign in derived Satake. So you have a complex reductive with a real form. Then it turns out the derived Satake give you not just a group, but some extensions, some interesting Z2 extension. You really need to consider this instead of involve the original groups in order to get the correct answer. Otherwise, you just, even in the case of SO2R or PGO2R, you really need to use these kind of extensions to get the correct answer.
Thank you.
So can I ask again, yeah, about this diagram? So can you again explain the role of causal duality there? So you said that this D, I mean,
Yes.
conjecture D.
Yes.
This is actually a causal duality.
Yes. Yes.
But somehow hard to think about it. So the groups GX check and GN check.
Yeah, they are the same. So GNX and G, they are the same. So therefore, here is nothing deep here. So once you, well, the difficult thing here is here. If you can have some construction where you can show that it's like this, and then the causality, you only need to check some cohomology shift.
I see.
Yeah, just like the case of complex group, you have a G, the dual with cohomology shift 2, and here is G cohomology shift -1.
So it's essentially saying that these two graded representations differ by some shift, and maybe
yes. So in particular, if you forget about those grading, you get this conjectural representation from this
I see. And also, maybe this relates to the very last thing you said, but in this derived Satake, as we proved it with Misha Finkelberg, so it was this key feature that when you consider the global cohomology functor on the derived Satake, then this corresponds to this restriction to constant slice, this sort of Whittaker reduction. So you have this.
Yes.
Right. So you have this coherent shifts on G check, and then you can, such a shift can be restricted to constant slice. And then we also do like loop rotation equivariant version, and it's quantized thing.
Yes.
With the reduction. So is there some analog known and expected here?
I think it's expected there should be a similar things here. So you have this Hamiltonian G space. It maps to it maps to G check. Then you can restrict the constant slice. Oh, then.
So it's just moment map, and then
moment map your constant slice. Then you can base change. Then there should be the cohomology should be this base change too.
And you can so in this last thing you wrote, so on the dual side it also corresponds to something, right?
Yeah, here this is quite mystery to us. For example, how to define cohesion on this kind of thing, and how to think about this. I don't know, so I have to think about this more. Maybe
I have a quick comment. Yeah, if you do it on the dual side, you take the constant slice of this M check, what you'll get is the group scheme of regular centralizers for SPN.
Okay.
Yeah.
Well, then looks good.
May I ask for clarification? Because if you do T star of that space, I think the image of the moment map doesn't intersect the Sloterdijk slice, the constant Sloterdijk slice.
You mean where? You mean here?
When you do GL2N with SPN, I don't think the regular nilpotent, for example, lies in the image.
Yeah, because actually no, because it has something to do with, or the real form is not split, so that's why you're right. So you have to. So we didn't check this, but you somehow see this. It has something to do with this quaternion, and you have this degree 4 thing. So if you do the equivalent cohomology computations, you will see this. But how to interpret this in terms of the moment map is maybe you don't need to. You can restrict to a regular this slice constant. You have to restrict to something else.
Yeah, perhaps like you still have the open nilpotent orbit, kind of maximal nilpotent orbit which lies in the image, and it has its own slot of slice and so on.
Yes, I think you should replace use that one.
There are a few comments in the chat.
So how to read? I can't read the comments.
I can read my question. I mean, it was also about this example, the symplectic one. So sort of in terms of periods, I think it's also given by the linear period. Does that not work for this M check thing?
No, I don't think they're quite dual, Tony. I think the dual of that linear period is something induced. You take something on the symplectic group and then induce it.
Yeah, just quick comment. We find this interesting that so some of this I mentioned this has something to do with some special value. So we check this. So Yanis has a list, and somehow in this case, it's really the special value is really kind of twice of the case of the complex group. So that's why. And somehow you see this double from this real picture because you have quaternion instead of complex number. We find this kind of interesting.
And what does it mean at the end that it's not tempered?
Well, you can look at well, in the PID, you can look at the Plancher measure for this, and it supports there's some or spectral restriction of the unramified part of the L2 function. This you'll see some non-tempered parameter there.
Okay, and so the other comment was over local field, linear period is equivalent to the Shalika period in the sense of spectral theory. For L functions, somehow Shalika period is better.
Oh, there's the comment or the okay.
Yeah.
I don't know much about theory, so still learning.
Can I ask a question about, so on one of the early slides, you were talking about per sheaves on this Lx mod L plus G. Did you actually mean that in a literal sense?
You mean here?
No, like much earlier. When you were talking about, when you were saying that there was a category of perverse sheaves.
Okay. Yeah. Yes. I think you can define this perverse. You mean this here?
Yeah. How are you defining that?
Yeah. There's no. Well, there's no canonical T structure here somehow because usually you think of this as some pro, and there are different type of pullback you can use to define this category. Yes, there are several versions of pervert T structure on this guy, and I'm not very. There's just one of them. So.
Why does one exist at all?
Oh, why they exist at all?
Yeah.
I think it follows from the construction how to define this category, from the construction of this category. So I think the basic example, maybe this you just consider some G action on some vector space. You choose the loose space of the vector space and consider L plus G acting on this space. You think about and how to define this category. And from the definition, you see that somehow you involve some smooth pullback, taking limit over a fine smooth pullback, and then there you see that you can define some T structure, but depends on how you normalize the pullback.
Mm-hmm.
All right. So if there are no more questions, let's thank Tsao-Hsien again.